Okay, welcome to day 4 of Unit 7. We've been working on vectors for the first 3 days. Today we're doing something new called polar coordinates, but it is connected to vectors. Key down. So I want to plot the point 7, 4. What we've been dealing with probably your whole life in algebra class are the coordinate plane, Cartesian coordinates, or something called rectangular. They're just x's and y's. So 7, 4 is the point right here. I'm going to call this point A. 7, 4. So my question is there another way to call that point A besides 7, 4? And guess what? It can't be done. There's no other way to write that point because point A can only be 7, 4. There is no other way to write that point other than 7, 4. So what makes Cartesian coordinates special? Well, what makes them special is that there is only one unique way to name a point in what we call rectangular or Cartesian coordinates. XY is XY, and there's no other way to name it. So today we're going to do something else called polar coordinates. Not X's and Y's. It is a different way of graphing points. You see over here this grid. Kind of looks like a dartboard or a radar screen. It's not square like the other one. So what we're going to pay attention to are two features on this called r and theta. Points won't be x, y anymore. They will be r, theta. R stands for the radius or the length or distance from the origin 0, 0. And theta is the angle of rotation from the positive x-axis. If you look on this graph, there are concentric circles and there are some diagonal lines. Each concentric circle represents a farther radius away from the center, and the lines represents the angles that you would rotate at. So how do we plot points? Well, there's two ways to do it. One way is what I call, first you do the radius and then you rotate the angle. So if I started here at 0, 0, I would go out of radius, length r, and then I would rotate whatever angle I wanted, and I would get the point r, theta. Another way to do this is to do the angle first and then go out the radius r. So what I would do is I would find some angle line first, and then I would go out on that angle line. I would go out at distance r on that angle line, and this point here would be r, theta. No way is better than the other. Sometimes I do the angle lines first just because I'd like to find out what my angle is. So as an example, I'm going to plot the point 5, 60 degrees. This is not an x and a y, it is a radius, angle theta. So I'll do it one way by going out 1, 2, 3, 4, 5 is my radius, and go rotate to 1, 2, right here is 60 degrees. I'm going to call this point A. It is the point 5, 60 degrees. That's what I did. Another way to do that, excuse me, I'll do it in red, is define the 60-degree angle line and then start at the origin and go out 1, 2, 3, 4, 5 down that 60-degree angle line. Either way, it's the same. So right now I have the point 5, 60. But are there other points, other ordered pairs for those points? Well, let's see. So as you can see, there are many different ways I can name that point 5, 60. I could take it 60 degrees and rotate another circle around, and I get 5, 420. I could do another circle again. I could do 5, 780. Or I could do backwards 360 and do 5, negative 300. Again, going back what we did in trigonometry, when I go counterclockwise, that is a positive theta, and when I go clockwise, that is a negative theta. So this angle here is negative 45 degrees, negative 90 degrees, and so on and so forth. Is there a problem? Absolutely. There are infinite ways to name a point. That could be a problem. So what makes polar coordinates special? Well, I give you any r comma theta. What can I do to that r comma theta? Well, I could do this. I could take the r and do theta plus or minus 360 degrees, and it will give me a theta that is in the same location as before, because adding or subtracting 360 is a full circle. You've changed the number of the angle, but you haven't changed the location. So is it possible to have a point that has a negative radius? What does a negative radius even mean? Well, we're going to plot the points negative 6, 30. So one way to do this is start at my origin and do a road going down the x-axis. Positive is 6, so negative would be negative 1, 2, 3, 4, 5, 6. And then I'm going to rotate 30 degrees from here. And here is point B. It is negative 6, 30 degrees. That's one way to do it. Another way to do that, and I'm going to do it in red, is to do, or let's say find, a 30-degree angle line, which is right here. And if I start at the origin, if I go this way, 1, 2, 3, 4, 5, 6, that point there is not the point I want. That point there is positive 6, 30. I want negative 630. So to do r equals negative 6, I have to go backwards. So it would be backwards 6. 1, 2, 3, 4, 5, 6. This whole line here, the 30 degree and the 210 degree, make one line. 30 degrees is positive this way and negative that way. So are there other ordered pairs for this point? So other ways I can name that point, negative 630, is to pick the angle line that it's on. It is definitely on the 210-degree angle line, but with a positive 6 radius, or instead of positive 210, it could be negative 150 degrees. That's the same angle. So 6, 210 degrees, or 6, negative 150 degrees is the same point as negative 630 degrees. So what did I do? I took my r and made it opposite, and I changed my angle by either adding or subtracting a half circle. So if you are given an r comma theta, what can I do to it to get it in the same spot? Well, I can do this. I can change it to a negative r, and whatever angle I have to add or subtract 180 degrees. Why 180 degrees? Because it's half a circle away. That's what a negative radius does. It uses the other half of the circle. Okay, so basically your whole algebraic life, you've been dealing with Cartesian or rectangular coordinates, x's and y's, your calculator has mostly been in function mode, and you've been using x's and y's to make equations. This is what you've been doing like kind of your whole life, or what we've been doing all year. As opposed to what we're going to do today, and we're going to do things in polar mode. So we're going to change our calculator, and I'll do this in a minute. We're going to deal with r's and thetas, not x's and y's, and our equations will be based off of x's and y's. Okay, on the bottom of the graph you can see we have a point on the graph, x comma y, or it can be r comma theta. Hopefully this picture looks familiar to what we did with vectors. Okay, I'm going to look at the calculator for a minute, and if you go, here's your normal calculator. If you hit the y equals, you see y equals blah blah blah. You'll put in whatever equation you want. That's what we used to do. What we're going to do now, we're going to change this mode. See, right now I'm in function mode. I'm in degree mode like we should be, but I'm in function mode. We've been doing functions for a year. I have these other modes. We could have done sequences before, but I chose not to. What we're going to work now is polar mode. It's a little bit different. So when I get out of here, I hit y equals. I don't see y equals anymore. I see r equals, because we're going to deal with r's and thetas. Okay. As you can see, this is how we write things, and hopefully this picture looks familiar to you. I want to show you how we do it. Okay, so if you look at this diagram, and I draw just an XY grid, we have this picture that we've done before. Vector V, and angle theta, and then if I break it down in components, I have this. This is the y component, this is the x component. As you can see, this picture looks very similar to the coordinate picture that we had before. Okay, sorry if there's a little glitch in the video. I thought I had it going right, but we'll continue. I'm going to look at the calculator for a bit. So here's a calculator, and if I go to mode, when I'm in function mode, the calculator looks like this when I hit y equals. I see y equals. But if I change the mode to something called polar mode, when I get out of here, I hit y equals, it says r equals, because we're going to deal with r's and thetas, not x's and y's. Okay, on the top you see our picture of point xy, or r's theta, and I've redrawn it using vectors because it's basically the same picture. Except vector v is now replaced by radius r. I still have an x component, I still have a y component, I still have an angle theta. It's all the same, so they look very similar. With that said, I'm still using these big four equations. And here's these big four, and here are the other two. These are the equations I'm using all the time. Same equations I used before, except instead of calling it magnitude, I'm calling it r radius. Remember, make sure you match the quadrant. You do inverse tangent, and you get an angle on your calculator. Make sure that quadrant of that angle matches the quadrant of the original points. Okay, it's not any different. I put things in radians too. We're really only going to use degrees in this unit. Okay, on this page we're going to do some examples. I'm going to give you an x and a y value, and you're going to convert it to an r and a theta by using the first two equations of r equals the square root of x squared plus y squared, never use negative numbers in this. And inverse theta equals inverse tangent of y over x. You have to use negatives when they appear. After that, I'm going to convert them from r theta into r negative theta by subtracting 360 degrees from the angle. And then lastly, I'm going to convert it into negative r theta by making my r negative and subtracting or adding 180 degrees to that angle. As you can see, I've done the first part of example A by converting x and y into r's and thetas by doing my two formulas, and 3, 4 turns into the point 5, 53 degrees. 53 degrees is in quadrant 1, which matches the points. I took that 5, 53 degrees and changed it into 5, negative 307 degrees by subtracting 360 degrees from that angle. Negative 307 degrees is in the same location as 53 degrees. It has not changed. And finally, I wanted to change it to a negative radius, so I made the radius equal to negative 5, and I added 180 degrees to give me an angle of 233. I could have subtracted 180, but I like having a positive angle in one full circle. Okay, here's example B. Again, the first thing I did was figure out the r and the theta. I do not put in negative numbers when I do the r. It does not matter. I got 5, 143 degrees. When I did the inverse tangent, I actually got negative 37 degrees, but that's in quadrant 4, and I didn't want quadrant 4. I wanted quadrant 2. So I made sure that this angle was in quadrant 2 by adding 180 degrees. Second part, I made it r negative theta by subtracting 360, and I made it negative r theta by adding 180 to the angle. And here are my examples C and D. I did my r and my theta. I converted it to r negative theta, and then finally negative r and theta. Notice on part D, I got negative 27 degrees, which is in quadrant 4, which is good. But I could always add 360 to it if I don't like having a negative. So I added that, and I said it was either 6.7 negative 27 degrees or 6.7 comma 333 degrees. Okay, now I graph all the points, A, B, C, D, in both Cartesian and polar coordinates. Obviously, the Cartesian is very easy. A, B, C, D. There's no other way to name them, and there you go. The polar is a little bit more work, especially since you have to guess where the angles are at a little bit. 53 degrees, 143 degrees, 333 degrees. You have to kind of ballpark it a little bit. And I count out my radius from the concentric circles. And if you notice, the points A, B, C, D in red are exactly in the same location as they are in blue. It doesn't really change. They just have different names. Okay, we're going to do more practice, except everything I'm going to give you is going to be an original r comma theta, and we're going to manipulate it into r's and different thetas or negative r's and thetas, and then finally changing it back into the Cartesian x's and y's. I'll go through some examples. Okay, for example A, I took my 5, 120 and converted it to 5, negative 240. And then to make it a negative r, I made it negative 5, 300. And then I converted it into x's and y's by doing x equals 5 cosine 120 and y equals 5 sine of 120. I'm going to go through the rest of the examples after I pause the video, and you could check your results. Okay, as you can see, I did examples B through H by doing r negative theta, negative r theta, and then x and y's. If you want to see the computations for everything, they're on the notes that are on the portal, the handwritten notes on the portal that you can look at. Please feel free to pause the video and compare your answers. Okay, now we're going to plot all these points. It's more practicing using the polar grid to plot points. So my first one is going to be 5, 120. I'm going to find the 120 degree angle, and I'm going to go out 1, 2, 3, 4, 5, and that is point A. Point B is 6 and 240, so I find the 240 degree angle, which is right here. And I go out 1, 2, 3, 4, 5, 6. That is point B. I'm going to pause the video and then do the rest of the points. And as you can see, I plotted the rest of the points. I'm going to make this one a little bit neater. That's point F. And there you go. Please feel free to move to the last page. Okay, for this last page, we're going to do things on the calculator. So my handwriting probably won't be nearly as neat, but we'll try our best. We're first going to change the mode to polar mode like we did earlier. So I'm going to do that by bringing up the calculator and going to mode. And my calculator is in polar mode, so I'm good. I'm going to get out of here. What happens when I press the Y equals key? The Y equals key is right here. Well, let's see what we get on the calculator when we hit the Y equals key. Again, I don't get Y equals, I get R equals. So let's see. You get R equals, not Y equals. What happens when we hit this variable key? This key that's right over here. That's right underneath mode. It says xt theta n. Well, let's see. Bring up the calculator. If I hit that variable key, I don't get the letter x like I used to. I get the variable theta. That's the difference. We're using r's and thetas. So we get theta, not x like we used to. So when we're in polar mode, we're going to have r is a function of theta, and our variables are theta and r, where theta is the input and r is the output. But we write ordered pairs as r comma theta, which is kind of reverse of x and y. X and y, x was the input, y is the output. This is the other way around. Theta is the input and r is the output. And we're going to try an example on the calculator where we're going to put in r equals 8 sine theta. I'm going to pause the video now. So I'm going to put this into the calculator of 8 sine theta. So just 8 sine, not the x key anymore, it's the theta key. And according to my instruction, I'm going to hit zoom 6. The zoom key is way on the top here. I'm going to hit 6. And I get this funny looking graph that looks very oval in shape, egg shaped. Celebrate Easter. But no, that's because the way the grid is looking, because it's negative 10 by 10 on both x and y axis. I'm going to go zoom number 5, and that will square up the picture. And look what we get. We get a circle. And if you notice, I have the tracer on, and it draws a circle twice. Let's go through why this happens. Okay, as you can see, the graph was a circle, and a circle's not a function, but we're not in function mode, we're in polar mode. We're going to be able to draw weird graphs when we're in this mode. Circle is an example of one of them. I'm going to complete this table, but I'm going to use the table that we use on the calculator like we did when we were doing sequences, and I wanted to see like the first 4 terms or so on and so forth. I'm going to have the calculator do all the calculations for me by using this whole table setup thing that we did before, except I'm going to do the table setup, start at 0, and do my delta table or my increments by 15, because if you look at the angles in the table, they're not always by 15, but if I always go by 15, I will get all the, I will get all the angles. I think they are by 15s. Okay, so I'm going to pause the video so I can bring up the calculator. As you can see, I have the calculator up here now, and we're going to make sure that we have our equation here, y equals 8 sine of theta, and we do. And I want to set up my table, so I'm going to do the blue second window, which is a table setup. And I'm going to start at 0 in my delta table with 15. And when I want to see the table, I'm going to hit second graph, and I get to see the table. And I get to see all those R values for those inputs of thetas. And I'm going to complete the table by hand, writing all the decimals to one place. As you can see, I used my calculator. I completed this whole table. Now we're going to start plotting some points. First one is going to be 0, 0. 0 angle, 0 radius. Right there in the middle, origin. Angle 15, going out 2.1. Angle 15, 1, 2.1, and there's a dot. And then I'm going to do 30 and 4. So here's 30 degrees, 2, 3, 4, and so on and so forth. I'm going to complete the rest. So as you can see, I did the first half of the table by all the red dots. Now I'm going to start doing the second half of the table. I'm going to change the color to yellow dots. And we're going to see how this is going to change. Because the first one I have to do is 195 degrees negative 2.1. Well, here's 195 degrees, but this would be positive 2.1 if I go towards the 195. I have to go backwards, and guess what? It's right over that red dot that we had before. 210, negative 4. Well, here's 210, and back negative 4 is again over that red dot. And you can see all of these for the second half are going to be over the red dots. So I'm finally going to draw the circle connecting the dots. So I'm just going to start from here, do the best I can. But that is my circle. It's okay. Technically, I would have to draw it again to go over those yellow dots that would be created the second time around. But that's why you saw my graph of the circle being drawn twice when you saw the little cursor. Okay, these are the end of the notes. You can look at the handwritten notes. Thank you.